When you collect data, is the variation in your data just due to chance, or is it due to one of the variables that you're actually testing? And so the first thing you should figure out is what do all these variables mean? So the first one, this right here, stands for chi-squared. And so this was developed way in the early part of the 1900s by Karl Pearson, Pearson's chi-squared test. So what is this then? That is going to be a sum. So we're going to add up a number of values in a chi-squared test. What does the O stand for? Well, that's going to be the data that you actually collect. And so we called that observed data. And then the E values are going to be the expected values. And so if you're ever doing an experiment, you can actually figure out your expected values before you start. And then you just simply compare them to your observed values. Let me give you an example of that with these coins over here. Let's say I flip a coin 100 times and I get 62 heads and I get 38 tails. Well, is that due to just chance, or is there something wrong with the coin or the way that I'm flipping the coin? And so the chi-squared test allows us to actually answer that. And so what I'm thinking in my head is something called a null hypothesis. And so if we're flipping a coin 100 times, and I think I said 62 heads and 38 tails, well, that would be the observed value that we get in an experiment. But there'd also be expected values, because you know that it should be 50 heads and 50 tails. And so you use something called a null hypothesis in this case, where you're saying that there's no statistical significant difference between the observed values and the expected frequencies that we expect to get, and then what do we actually find. And so it's cool, chi-squared, because we can actually measure our data or look at our data, and we can see, is there a statistical difference between those two. The best way to get good at chi-squared is actually to do some problems. Before we get to that, there's two terms that I have to define. One is degrees of freedom, and then one is critical values. And so the whole point of a chi-squared test is either to accept or reject our null hypothesis. And so you have to either exceed or don't exceed your critical value. But first of all, we have to figure out where that number is in this big chart right here. First thing is something called degrees of freedom. So since we're comparing outcomes, you have to have at least two outcomes in your experiment. So in this case, if we have heads and tails, we have two outcomes that we could get. So we'll say that's 2. And then you simply subtract the number 1 from that to get the degrees of freedom. And so in this case, we have 2 outcomes minus 1, and so we would have 1 degree of freedom. Now you might think to yourself, why isn't there a 0 on this chart? Well, if you just have one outcome, you have nothing to compare it to. So that's an easy way to think about that. So we figured out that there is 1 degree of freedom in this case. Next thing you're looking at is for a critical value. This is the 0.05 value. And so that's going to be this column right here. So the first thing you do is you find the 0.05 value, and you don't worry about all the other numbers. So that's 3.841 is something I just know because it means that I'm in the right chart or I'm in the right column. A way that I explain this to kids is that you can think of that as being 95% sure that you're either accepting or rejecting your null hypothesis. And you can see that our critical values get higher over here. So you could think as we move this way, if we really want to be sure, we'd have to exceed a higher critical value. So what's our null hypothesis again? Null hypothesis, no statistical difference between observed and expected. And so we either accept or reject that value. So in this case, our critical value would be 3.841. And so when you calculate chi-squared, if you get a number that is higher than 3.841, then you reject that null hypothesis. And so there actually is something, aside from just chance, that is causing you to get more heads than tails. And if you don't exceed the critical value, then you accept that null hypothesis. And this is usually what ends up happening, unless you have a variable that's impacting your results. And so let's apply this in a couple of different cases. So this is my wife here. I asked her to flip a coin, and so I asked the statistics teacher, how much data do you have to get before you can actually apply the chi-squared test? And Mr. Humberger said something magic about 30. And so I wanted to exceed that number in each of these experiments. And so this is my wife down here. This is her hand. And what she's going to do is she's going to, let me get a value you can see, is she's going to flip 50 coins. You can see she's really fast. So she's flipping 50 coins, and then she's sorting them out. And so if we look at that, the first thing, even before you collect the data, is we could look at the expected values. And so we've got heads or tails. And so if you flip 50 coins, how many do we expect to come up as heads? The right answer would be 25. And how many would we expect to come up as tails? 25 as well. If we look at our observed values, well, let's look down here. How many heads did we get? So this would be 25. So that'd be 28 heads. And how many tails did we get? So that'd just be 22. Okay, so now we're going to apply chi-squared and come up with a critical value. And so what does that mean? Well, let me get this out of the way. So we're going to take our equation, which is O minus E squared over E, and we're going to do that for the heads column, and then we're going to do it for the tails column. So we've also got O minus E squared over E for the tails column. And so our observed value is going to be 28. So it's 28 minus 25, which is expected, squared over 25. Now this sum means that we're going to add these two values together. So I'm going to put a plus sign right here. Now we're going to do the tail side. So what's our observed is 22 minus 25 squared over 25. So you can do this in your head. 28 minus 25 is 3. Square that is 9 over 25 plus 22 minus 25 is negative 3 squared is 9 over 25. And so our answer is 18 over 25, which equals 0.72. Okay, so that's our chi-squared value for this data that we just collected. Now let's go over here to our critical values. Well, we said that we had 1 degree of freedom because there's 2 outcomes. 2 minus 1 is 1. So we're in this right here, in this row right here. And then here is our magical 0.05 column. And so our critical value is 3.841. And so if we get a number higher than that, we reject our null hypothesis. We didn't. So we got a value that is lower than that, 0.72. So that means that we have to accept our null hypothesis. That means